Okay, so let us start. The second talk this morning is by BÜHLMANN from ETH in Zurich. We will speak about robust, generalizables on causal-oriented statistical machine learning.
Thank you very much for the introduction, also for the invitation to speak here. It's of course an honor to speak at this conference, and I also would like to thank the organizers for having put this huge effort into making this conference running. So here's again the title of my talk. I would like to first acknowledge my main collaborators of the research I'm explaining or describing a bit today. This is Dominik Rothenhäusler, Niklas Pfister, who is in the audience, Yancy Chen, Jonas Peters, and Nikolai Mainshausen. Statistical machine learning, this is in my title. We have multiple of terabytes of data nowadays, we all know that, and we want to extract something useful, leading to reliable actions, decisions, better understanding, more insight. And in modern terminology, people talk about robust and interpretable artificial intelligence. So AI is everywhere, also in the news. And this is an interesting article which has been published by Michael Jordan, who is in machine learning statistics at Berkeley. Artificial intelligence, the revolution hasn't happened yet. This was published in 2019, and I still think in 2022, I very much agree with this statement. So there are plenty of good realistic examples where machine learning may be quite useful. Yesterday we've heard a talk also on deep learning by Stéphane Mallat, you know, image classification, speech recognition, what is on your cell phone. These are good examples where machine learning works quite well. Here is another one which I just want to expose to you. Machine learning is set to detect driver drowsiness to reduce road accidents. Okay, so there's a system in a car. It's potentially a small cost, right? It costs something, but maybe a huge gain, because we just compare it against having nothing, right? Even if the system is not very effective, it may be a bit better than nothing. In a way, this is the modern version of the Totman pedal in a railway locomotive. If you don't know what a Totman pedal is, so the railway driver has to signal about every 30 seconds that she or he is still awake. And now the question is different. Would this new ML system be actually better than the Totman pedal? And this must be evaluated very carefully. That's not so clear at all. So there are many critical examples, in my view, about AI and machine learning. Here is one which you also can read a lot, AI in legal decision-making. I'm not working in this area, but I see many major issues here, ethics and also reliability of these predictions. Here's another area which is quite critical. Here I have my own personal exposure and research. Machine learning in public health, in medical care. So this is a picture in an intensive care unit, and we have nowadays just a lot of data which is collected in intensive care units, and people make predictions. It says, okay, in 5 hours from now, you will have developed sepsis. And the question is, do you really trust these predictions? I'm not. I would like to see additional uncertainty of these predictions. Just on the high level, it's actually interesting that there are good initiatives in this area. The FDA, which approves the drugs, right? They have also a new program to certify algorithms, machine learning systems. So it's against the action that everybody can just put in the Wild West a new machine learning tool in a hospital and it will make predictions. So in the medium run, hopefully there will be certificates and only a certified algorithm or machine learning system is allowed to be used in hospitals. So that is a good development. If you think more in terms of methods, can we actually do something? I still think it's challenging, but it's interesting, and perhaps it needs more statistical ideas, and of course statistics is my own background, so I try to contribute something from my own background. So statistical ideas, among very many. Today I just want to reconsider generalizability, robustness, and interpretation of these machine learning algorithms. Let me start with what we call the Stats 101 course. This is the introductory course in statistics. It's about single data generating distribution and statistical inference. And I start with a quote from two famous statisticians, Mosteller and Tukey. They wrote in 1968, "One hallmark of the statistically conscious investigator is her or his firm belief that however the survey, experiment, or observational program actually turned out, it could have turned out somewhat differently, right? There is noise, and if you repeat the experiment, you will not see the same thing." So of course, in statistics, we have a long history how we model this paradigm. So we have data, we have values, these are just numbers. They're denoted by little z1, z2, zn. And we model them as outcomes, as realizations of random variables. They're denoted as cap c1, cap c2, cap cn. Then in addition, you put a model of these random variables. The simplest one is IID, independent, identically distributed. It could also be from a stationary distribution, but there's an underlying probability distribution mechanism in the model, and this is denoted as P0. So P0 is the data generating distribution. Okay, and then the classical goal in statistics is, let's do inference. Let's say something about a functional of this data generating distribution P0, right? That's very classical, the mean, the variance, quantiles, and so on. The history is very, very long, dates back to, in my view, Al-Kindi, who was maybe the first statistician in 800 after Christ. Then Grant and Petty in UK, in England, they put out the first life table. Then there are many famous names here. And most of this is about generalization to new data, which comes from the same distribution P0, which has been observed and used in the training phase of your machine learning system. So in folklore terms, it's about a new patient with the same characteristics as in a representative study. That's classical statistics. So I want to generalize to new data generating distribution. I want to generalize beyond the P0 which generates my data. So the setting is as follows. I have data, it's observed from this generating distribution P0, and I want to say something about a new distribution P prime which is different from P0. Now, of course, if you see that, you say, well, this is totally ill-posed, this is impossible to do. In general, of course, this is impossible. Nevertheless, people have made quite a bit of progress on this problem under different wordings like distributional robustness, transfer learning, domain adaptation, transportability, and so on and so forth. So let me go one step further, which is actually a bit more realistic in nowadays world of the data. So let's assume the setting where the data comes from various different data generating distributions. You can think of different subpopulations. You have 5 different countries. These are 5 different subpopulations, and each of these 5 has its own data generating distribution. So in my notation, I have heterogeneous data from various distributions, PE, and in my presentation, E is the notation for an environment, an experiment, or a subpopulation, and they come from a space script D. This is what you observe in the data. These are your observed subpopulations, your observed environments, your observed sources. And now the more general question is, we want to say something about a new PE E prime, where E prime is not among the observed subpopulation. So you have 5 countries, and you want to say something about the 6th country you've never seen in the data. So people call this external validity, and of course it's very relevant. I might give you a couple examples in a minute. So we observe things in this script D, these are the observed subpopulations, but we want to say something about script D complement. So Niklas Pfister, who is here, he will also talk about this today after the break. So there are very many examples where this is really important. So here's the first one, multi-center study, say, and this happened, COVID-19 vaccine development. So what has been done? We have a lot of different subpopulations all over the world, multi-center study, but you're not interested in what happens to exactly these persons which were in the study. You're interested in the new person who were never in the study, right? So you want to look at new, different outside study subpopulations, and I'm quoting here from an interesting paper which says, instead, for decision making, whether this is a good vaccine or not, the users typically have a new target population in mind, which you've never seen. So Cox, who just recently passed away, he was a giant in statistics, he wrote in 2001, the success of a theory is best judged from its ability to predict in new contexts. It's not about what you've seen in the data, it's about what you've never seen before. And here's a cartoon illustration to make it clear what I have in mind. I'm not working on this problem, but this is an autonomous system, self-driving cars. You train these systems on very many design scenarios. That's what's going on. So you train these machine learning AI systems of self-driving cars in very many designed scenarios, but you want that the system works well in a new scenario which the system has never seen before. So you want to generalize to a new context. Okay, so this is important as an empirical fact. Standard machine learning techniques, standard deep learning, despite its success, is not good if it goes to external validity. So here's a study from the Wild Stanford database. It has been published a year ago. So we have a couple of data sets on the left column here. And these large data sets, they have different subpopulations. And now you can train your algorithm without a certain subpopulation, and you try to predict a new one. Then you have different performance metrics. And then you have in-distribution performance and out-of-distribution external validity performance. The numbers mean large is good. And so on the first data set, we have an in-distribution performance. How do people do that? They use what's called cross-validation. You delete a couple data points and try to predict them. Within the data which you have, the in-sample performance and in-distribution is 47. Then out of distribution, in new context, it drops to 31, and so on. The next one is 93, it drops to 73. And if you go through the whole study, on average, there's a 26% performance loss if you go to external scenarios which you've never seen before. So standard ML techniques, they're good for very specific tasks, but they're not so good if you use them in a hospital. It's trained in a hospital, and you want to use them in the next hospital, which is different. So how can we try to address the issue of this external generalization? And of course, there are many approaches. Today, I want to show you a bit two points here. The first is distributional robustness. The second one sounds exotic. It's called causality. This is a dangerous word, I think. This has nothing to do with true underlying causal things in the real world, but it's a technical term in the literature. And I want to indicate the connections between these two fields. Let's start with distributional robustness, because this is maybe a bit easier to capture what's going on. So what we have in mind, or the setting is, we have what's called a response variable, y, right? Whether you will get a disease or not, or it could be continuous or discrete. And you have covariates, features, they're denoted by x, they're d-dimensional. And we have data di, yi, comma xi. I is the index of the data point. It could be IID, it could be stationary, and so on and so forth. Now, what is a distributionally robust regression of y versus x? So let's just look at linear models. So you want to explain y as a linear function of x. So this is a multivariate quantity. I just write x beta. And you want to find this unknown parameter vector, this regression parameter vector beta, by optimizing what we call a risk, an expected squared error loss. But now we do this over many distributions which are within a ball of radius rho around a p0. So p0 is my data generating distribution, which I have in the training phase. And then I look somehow at the supremum here over all distributions p which are in the rho neighborhood of my data generating distribution. And I try to find the parameter which optimizes worst case risk. So what's going on here is that people postulate a metric, Wasserstein, F divergence, and so on. And in practice, P0 is the empirical distribution which you observe, and then you can solve this program. So this goes back to classical statistical robustness, Huber in 1964. People in robust optimization look at this problem, and recently quite a few people in statistics machine learning take this combined view of robust optimization and statistical performance. Now you say, okay, this doesn't have much to do with machine learning, but of course you can do this non-linearly, and this is what people do. You try to find a function f of the features, a neural network, a random forest, which optimizes worst case risk within all distributions p which are rho apart from p0. So this is actually very much related to the active field of adversarial machine learning, GANs, and I'm referring here to Ian Goodfellow, who started this sort of research to make deep learning, machine learning algorithms much more robust. They're not only good at P0, they're good in a neighborhood of P0 with a metric rho, with a radius rho. So what are the main issues here? The metric. You just simply postulate a metric, like Wasserstein, but it's not learned from the data. You just say, okay, I want to be robust with respect to this metric. And then you also have to choose a radius rho. If rho is very large, you're very robust among many distributions, but you may have a very conservative procedure, which is not good in the neighborhood of P0. In particular, if you look at this distributional robustness, it may not work well if it's really a different domain. And this is a cartoon illustration. This is maybe my P0. This is another P. They're far apart. If I would just take a Euclidean metric, right, just round circles, I would need a large rho to capture the red distribution. It does not exploit that here there is a directional relation, right? It just simply postulates the metric, and it doesn't exploit any structural directional relations between the different subpopulations. So this is very much used in practice, distributional robustness. People do that, people solve that. They mainly look at computer vision applications. I'm sure many of you have seen this, digit recognition, and so on and so forth. So this is image classification. You can find a huge amount of numbers, and the reported success on external generalization, on new scenarios, on minority groups, and so on and so forth, has shown some success in computer vision applications, maybe also in speech recognition. This is a much less active field, at least in the academic community. But if you look how well these techniques have worked or performed on other problems, like in health, in medicine, in economics, it seems much harder and much more difficult. Okay. So this is just distributional robust optimization, distributionally robust statistical estimation. It's a good thing. It has some drawbacks if you really have quite different scenarios and subpopulations from which have directional information. So let me explain a bit what the other approach is, the other which I want to explain today. And interestingly enough, they will be related, and I will show you that. So again, causality, this is a technical term. It's another way to look at external validity. So this technical term, causality, what is it? We think that an oracle provides a model for the entire system. Okay? So we have a response variable y of interest. I have my feature variables, say x1, x2, x3. And of course, there are many hidden, unobserved variables which you have not measured. They can be very troublesome. So for example, in this picture, in this graph, you see y is influenced, this is how you read the graph, is influenced by x1, x2, but also by this non-measured latent variable h1. Okay, this was the oracle world, this is just a model. Then once you have the structure, this is for simplicity a DAG, it has no directed cycles. Then you specify function models on this graph. And how do you do this? This is very intuitive. So if you collect all the variables in the graph, these are my random variables in the system, y, the features x, hidden variables h, then I model every of these random variables, say the jth component, as a function of its parental variables, comma, error term, epsilon j. You do this for all the variables, and you assume in this model that these errors are jointly independent. So for example, y is a function of x1, x2, and h1, comma, error term, and all these error terms are jointly independent. This is called a structural equation model. It's quite mechanistic, it has good properties. Now some of you may have heard about Judea Pearl. He's a very famous man in causality, and he calls this structural causal models, and he makes the philosophical step that he claims this is actually the true underlying causal mechanism. We don't observe that, but it exists, and that's what it is. This is philosophical. I don't care too much about it. I call it a structural equation model. Mathematically, these are exactly the same objects. Doesn't matter. So once you have these structural equation models, and because of this joint independence of these error terms, you have nice properties, namely the distribution which is generated by this structural equation model, right? All these variables, it's a joint distribution, say P. It satisfies the Markov properties with respect to the graph. So I refer here to Stefan Lauritsen, who did path-breaking work, and also his book, who really educated a whole generation of statisticians and applied mathematicians. So this is a nice model. It has Markov properties with respect to the graph. So now you say, okay, if we have enough data, let's learn this graph, right? Let's try to learn the structure. And I must disappoint you, this is impossible in general. You cannot do that. It's very well known that you can only estimate the so-called Markov equivalence class of graphs. Different structures give exactly the same probability distribution. This is in particular troublesome in presence of hidden variables. And in folklore terms, it just means learning directions, what's called causal relations, is really troublesome. It's really kind of a bit impossible if you just have observational data. So why am I introducing you to these models? In my view, these models are interesting models to model perturbations. I'm interested in what happens if I perturb the system. And I introduce you to just maybe the simplest, is a very simple perturbation model, and it's called Pearl's do intervention. Okay, so I explain it to you. I have a graph, no hidden variables, I have structural equations. You know, every random variable is a function of its parents, comma error term. The error terms are jointly independent. So y is a function of x1 and x2, comma error term. Now I do an intervention at the second variable. I set the second variable, this is a random variable, I set it to a value, a numerical value, little x, like 2.7. And Pearl denotes this by do x2 equals 2.7. Okay. So what is the model? This is a model, it's not the truth. What is the model for that? Okay, it's quite plausible. He says, okay, if I manipulate at x2, there's no influence from x3 any longer to x2, right? I manipulate x2, so the influence of x3 is gone. So I break the arrow, which points into x2. This is a plausible step. And then you say, this is my new graph, and I put my structural equation model to the new graph. Okay, so the second variable is just this little x, this 2.7. And this little x propagates here through x1 to y, goes directly to y, it propagates through these structural equations. Okay, what do we have here? Dynamic propagation of interventions. If you intervene somewhere in the system, it dynamically propagates to the variable y, which I'm interested in. I think this is really good. This is a good property of these intervention models. But there is a huge assumption here, and this is called autonomy. In this model, as you see, we have the same structural equations. So it's the same f1, the same fy, and so on. So what this model says, you intervene, you change the value of x2, but everything else remains the same. And that is a huge assumption. That's not clear whether this holds in practice. However, if we want to do external generalization, we must extrapolate somehow. So we need to make some sort of stability assumption, and that's what it is. Okay, so now I claim we can do causal thinking for external generalization. With such perturbation models at hand, causality is giving me a prediction, a quantitative answer to a what if I do, what if I perturb question. It answers what happens if I put x2 to 2.7? I can compute that, right? And the point, of course, is the perturbation is not observed. If I would have this graph, have these functions, I could just simply do that. I refer to Pearl. He really influenced this sort of thinking a lot, and his book is also groundbreaking. So he really I give him a lot of credit for kind of paving this way that we can think this way. Causality is giving me a prediction, a quantitative answer to a what if I perturb question. Of course, he is not the inventor of that. I go back to Jerzy Neymann's potential outcome model. This is a cute little history. He published or invented that during his master thesis in 1923 when he was still in Poland. So potential outcome, really, this is this counterfactual language. It really is about what would have happened if we would have assigned a certain treatment. And this is really a milestone. But it is about what would happen if I perturb. Therefore, causality can be used to generalize to new scenarios. Again, say in medicine, what would happen to a new patient who is different, a perturbed version from the ones in the study. Okay, so you may think, okay, it's not too hard. I try to give you a very fundamental explanation why this is very different from what we're used to think. So let's try to predict an intervention effect. I have two variables, an x variable, a y variable. This is synthetic data. Of course, I made it up. A straight regression line fits this data very well, so I have a good model for this data. Okay. Now, I manipulate x and set it to the value -8. And I ask you, what is the prediction for y, the best prediction for y when you manipulate x to be -8? I give you 3 seconds. 1, 2, 3. And most of you, including myself, would have said, that's here, right? I fit my regression line. This is introductory statistics, right? And this is my best prediction. And that's the right answer if x causes y. If I manipulate x, I put it to -a, y will change according to the learned mechanism, which is the straight line. Some of you may have said, well, this is my best prediction. And this is the right answer if y influences x. If you manipulate x, nothing happens to y, right? if this is the mechanistic model. And if nothing happens to y, the best prediction is the mean of y, which is the red dot. And the challenge is really, how the heck can you make the prediction whether it should be here or there? Now you say, okay, this is just synthetic data, but this is actually real stuff. So we have been involved in prediction of intervention effects if you knock out a gene. So we have actually yeast. We look at the organism of yeast, and you knock out a gene, and you want to say, does another gene move or not? So here's an example. We measure the expression, the activity of an X gene and on a Y gene. We have data in blue. We fit a linear model. That's simple, right? I have this regression line. Then you knock out the X gene in the lab. The activity goes down. This is on the log scale, so there's an effect of this knockout. And lo and behold, the Y gene roughly changes according to the estimated linear regression line. This is another X-Y gene pair, right? You have an X gene, a Y gene. This is the observed data. You fit a regression line. There's some sort of correlation. You knock out the X gene. Its activity goes down and nothing happens to the Y gene. That's the other relation. And this is exactly what I explained with this synthetic data. And the challenge is, how the heck can you predict that? This cannot be answered with standard ML. Standard machine learning does not say anything about directionality. We'll have some results. I kind of briefly sketch them or indicate them a bit later. But let's make this now a bit more constructive and operational. I mean, I just gave you somehow a high-level overview what the problem is. And let me go back to this idea. Okay, let's look at heterogeneous data. I have multiple environments, multiple subpopulations. This is again the same notation. E is a subpopulation, or an experimental condition, or a perturbation. I have data X, Y. X are my features, Y are my responses of interest. They have a distribution, let's call it PE. For every subpopulation, I have a different E. Example, medical data from 13 different centers, hospitals. So this E is in this space script D of observed subpopulation. So my script E, what I observed, is labeled by 1, 2, 3, up to 13. And many, many large-scale applications have this structure. You just collect data from a lot of different subpopulations. Okay, the script D, that's important. That's the space of observed subpopulations. Now, how about external validity? I consider now many possible, but mostly non-observed subpopulations, perturbations, and they are in my notation coming from a space script F. So script F is much, much larger than script D. So example from script F, it would be the 13 centers, hospitals, which you've seen in the data, and many new hospitals out in the world. And so here's the pragmatic prediction problem, as usual in, say, machine learning. Predict Y given X, given your features, you want to predict Y, such that the prediction works well, is robust, replicable for all these many possible new subpopulations which you've never seen. External validity. Let's make it for linear models. That's a bit simpler. I tried to find the regression parameter vector which optimizes worst case risk over all these scenarios, subpopulations, which I have not seen in the data. Okay. So people call this robustness, as I explained a bit before. This looks very similar. And a few people say, well, hey, this is causality because it's about new scenarios, new perturbations, which you've never seen in the data. This is Pearl thing. Causality gives you an answer to new perturbations which you've never seen. Okay, so here is one of the main results, and I give this in a non-theorem version here. Actually, these two worlds, they're linked together, and this is quite exciting, I think. This is a fairly new development. And again, for simplicity in linear models, in a nutshell, the following is true. On the left-hand side, I do worst-case risk optimization. This is something we know quite well. Many people in mathematics understand this object. And on the right-hand side is what people call the causal parameter. This is a very exotic object. And the causal parameter, I just give you a bit details what it's meant to be. And so here's kind of a theorem which says worst case risk optimization equals causal parameter equals causality if, of course this is not true in general, if this script f, this space of future subpopulations satisfies some assumptions. Right? Otherwise it's not possible. But it's an interesting perspective because if we have this, we can maybe do more that sort of stuff which is much more well-known and easier than trying to estimate graphs from the data and things like this. Okay, let me explain this a bit more. So when is this true? When is this theorem true? So if you take a script f, now you need a model. What is your model for your perturbations? If the script f are all perturbations which do not act directly on y, but they dynamically propagate, as I explained a bit before, then this is true. And here is a picture what I mean by that. So these environments, these subpopulations, they're here denoted with an E. And this means I look at all possible perturbations which do not act directly on y, but they do act on x. So then this theorem is true. Worst case risk optimization over these perturbations equals the causal parameter. What is the causal parameter? I have my structural equation model. I look at linear models. It's just the parental variables of y. You regress y on the parents of y, and the regression parameter is the causal parameter. Okay. So the experts in the room say, yeah, well, okay, we know that. This even holds, and that's interesting, this even holds if you have unobserved hidden variables. That's quite surprising. Even if there are hidden variables out there in the world, this is still true if, well, you need a perturbation model. The perturbations are allowed to act on x, but they're not allowed to act on y, and they're also not allowed to act on h. Okay, but that's an interesting, promising fact. And you may wonder a bit, well, why is this true? And I want to give you a bit the history of that. There is invariance here built in, which is the implicit underlying main property in a way why this is true. I show here a picture of Trygve Havelmo. He was a famous person in economics. He later got the Nobel Prize in economics. And Havelmo in 1943 derived the following in my notation. If you have the autonomy assumption, that was my perturbation model, if I perturb, the structural equations remain the same. If you have that, then if you look at the conditional distribution of y and you condition on the causal variables, on the parental variables of y, then that conditional distribution is the same across all scenarios, all perturbations in this script f. They do not act directly on y and they do not act directly on h. So from a historical point of view, Havelmo already knew if I know the causal structure, the parents of y in my system, I can get invariance by simply conditioning on these parental variables of y. The conditional distribution remains invariant. So causal implies invariance, and a while ago we said, well, nowadays you have a lot of data. You can try to search for invariance in the data and then go backwards. And this is kind of our program somehow. So we were proposing that you look at invariance in the data and then say something about causal or at least robustness. And this goes as follows. Just very briefly, you search by statistical testing for a set of features, let's call it S star, such that the conditional variance, if you condition on these features from S star, remains invariant across the environments which you see in the data. Okay, this is not so hard to do. And then the question is, well, what is this S star? And actually S star equals the parental variables, what people call the causal variables, if the observed number of heterogeneity of different subpopulations is sufficiently large. If you see a lot of different subpopulations, it's good to identify the structure. So we call this inverted process invariant causal prediction. We had quite interesting success for this gene knockout problem, which I briefly introduced to you. So we looked at yeast. The question was, can we predict when you knock out a gene, can you predict whether another gene will move or not, whether the red dot will move down or whether it stays up there? In view of time, I'm not going into details, so a bit for the experts. This is an ROC type curve. If the curve goes steep up, that's good. And this invariance type technique is the red curve. This is a version of it, and this performed much better than other causal inference techniques, which were as good as random guessing. Random guessing was here in gray. What's important for me to say is we don't infer somehow the causal network in this organism. This is much, much too hard. But nevertheless, we can prioritize future experiments. Now you can just compute with your algorithm what is the most promising gene knockout, which you haven't seen in the data, and then you can just do it and check how good you are. Okay, I mean, I started quite a bit with AI and ML, and of course this is not machine learning. And I want to introduce you a bit more to this machine learning world, how we can make use of these ideas. So now I want to encourage various degree of invariance. I told you we're looking for invariance of conditional distributions. Maybe you want to have exact invariance, maybe you just want to have a bit invariance and you can kind of regularize that. And so the new, the environments which I denoted before with an E from this space script D, they're now outcomes of a Q-dimensional random variable A. And this is called an anchor. I'll explain that in a minute, why we call this an anchor. And now what you can try to do is, okay, let's make things stable when you want to fit a regression parameter. You try to find a parameter which optimizes residual sum of squares, but you regularize such that the correlations of the residuals across your different environments is small. So you want to make the residuals fairly uncorrelated over different subpopulations. You can do that. This is encouraging correlation invariance in a certain sense. This is not quite what we propose. We propose something slightly different. This is a bit more for the experts. We look at this projection on the column space of A, so it's just a linear projection. And then we propose what we call causal regularization. We estimate the regression parameter as follows. You take argmin of anti-projection residual length squared plus a regularization parameter gamma times projection residual length squared. Okay? So for gamma equals 1, if my regularization parameter gamma is 1, this is least squares, because this is Pythagoras, right? You can always decompose in anti-projection length squared and projection length squared. For general values of gamma, this is doing something. We call this causal regularization because of this invariance. Now, for people in machine learning and statistics, they say, well, we look on high-dimensional problems. If we want to add further structure and regularize it, you can do that. I can do an L1 norm penalty, another sparsity enforcing penalty, and so on and so forth. This is very easy. This is all convex optimization. I can also do non-linear neural network fitting random forests. It looks like, okay, I look for functions f which optimize the same thing, anti-projection residual length squared plus a regularization parameter gamma times projection residual length squared. So you can add invariance to many mathematical models and algorithms, and perhaps one should do, at least in some applications. Now the question is, well, why should we do this? And actually, I think we have interesting mathematical guarantees, which I try to explain a bit to you. So let's look again at the system. I have a y and x, I have hidden variables, and I have these environments. This is called the anchor variable. And I ask, well, in my modeling world, how would these anchors, these environments act on the system? And this is one version. The anchor variables, the environments, act on x, but not on h and not on y. And this is a very popular and well-known model in economics and econometrics. It's called the instrumental variables regression model. This is very much used, and people call A an instrument. It's just terminology issue. It's an interesting model. There's two large or big assumptions, namely A, the environments do not act directly on Y. Okay, maybe. But then also the assumption that A, the instruments, the environments do not act directly on H. How the heck can you know that? H is something you can even name what it is. It's hidden, right? So you bet on a huge assumption. Nevertheless, it's an interesting model. It has also been recognized with the Nobel Prize in Economics just last year. So Angrist and Imbens, they're people from economics, they got the Nobel Prize for their work with this instrumental variables regression model. It's actually interesting what the citation reads. Angrist and Imbens developed a framework showing how precise conclusions about cause and effect could be drawn from natural experiments. It's no designed experiments. It's not randomized experiments like in drug admission. It's just unspecific perturbations. Okay, so we were interested in saying, well, okay, this is this huge assumption that your A does not act on H and not on Y. So let's just assume it's allowed that it acts, right? A, my environment, can act on everything, on X, on Y, on H. And the only assumption what we make in this graph is that H is a source node in the graph. It's kind of exogenous, what people in economics would say. It's a source node in the graph. That's the only assumption, and that's the reason why we call it an anchor variable, because it's the source, it's the anchor of the system. This is a structure. Once you have the structure, you can put a quantitative model on the structure. For simplicity, I stay here linear. So I have my linear structural equation model according to this structure. And what comes from this A, from this anchor, comes exogenous from outside, M times A, also linear. So we call this anchor regression. Instead of instrumental variables regression, we have a new term calling anchor regression. So we allow that A acts on Y and H, right? So here. And then there's a problem. And that's why people didn't allow that, because then it's impossible to find the causal parameter. If you break that assumption, there's no way you can get this causal parameter. Okay, it will slow down. So you cannot get the causal parameter. Is this a real fire coming, or? And so that's probably why many people have not used this. They said, okay, this is not possible, so you should not use this sort of model. So it's a bit, okay, good. But the issue is, it still solves a worst case risk optimization. So even if you cannot find the causal parameter, the causal structure, it still leads to worst case risk optimization. And I want to explain that a bit to you. This will be my end then of the presentation. So of course I need to define to you what is the perturbation model. And so in this anchor regression structure, we have this model. This is my linear structural equation model. I have this exogenous term from the environment M times A. Now you should think about a perturbation on your system. We call these shift perturbations. And what we say is, okay, this exogenous contribution from the different environments, the different subpopulations, enters as a vector, call it V. It can be deterministic or fixed. And this V is technically in a space C gamma. But the important thing is, V is in the span of M. So it has the same direction than what you observed in the data across your different subpopulations. And this gamma here indicates essentially the L2 norm of your perturbation. So if you have a large perturbation, you have a large gamma. So I want to translate this into folklore terms. What is this perturbation model? The perturbation V in new test data have the same direction as the observed heterogeneity in your observed data. Why? Because it's in the span of M. And the perturbations could be much stronger in the test data than what you have seen in your training data, and that's the size of your perturbation gamma. That's what this perturbation model is. Suppose you see heterogeneity in the data along a certain direction, you say my perturbation also goes into the same direction. And in my view, this is the most natural extrapolation you can do. You have to extrapolate to something you've never seen before. So, okay, I keep kind of the geometric direction, what I observed in the data. And the other point is, the more perturbations and heterogeneity I see, the better I can extrapolate. Why? Because the span of M gets larger, right? If I have more and more environments, the span of M gets larger. This is very controversial in classical statistics. You want to collect nice data, homogeneous, but for learning something about the system, it's good to see many different scenarios and subpopulations. Of course, experimental scientists know this since a long time. They do many experiments under different conditions to learn something about the system. And so here is actually the detailed connection between this causal regularization and worst case risk optimization. And the theorem reads as follows: for any regression parameter beta, on the left-hand side, I have worst case risk optimization over all perturbations in this class C gamma, and this equals exactly the causal regularization objective criterion. So it's anti-projection residual length squared plus gamma, the same regularization parameter as the strength of the perturbation times residual length squared. So I'm coming soon to an end, but I want to make this point very clearly. I showed you distributional robustness. I said, okay, how do you do this? You postulate a metric, Wasserstein, F divergence, you take a radius rho, then you have the ball in that metric, you want to be robust in that ball. That's the picture here. Now this here is also distributional robustness or robustness over perturbation, but the metric becomes ellipsoid. Why? I have learned it from the data. I've learned it over the different heterogeneous environments, and that allows me to go into certain directions with my metric and achieve robustness according to flat directions and full volume directions. So this is very important in high dimensions and gives also interesting results. So in my view, the things that we can put robustness and causality together through this theorem, that's interesting, but in a way what I want to say is, if you're just interested in distributional robustness, you may want to work on new areas where you can say, okay, I learned my metric from the data. This is much more powerful in higher dimensions if you have learned the metric where you want to be robust, than just simply postulate a metric and take a radius rho. One can indeed improve prediction. I don't have time to go into that. I also skip this part. This is in fact quite interesting. You want to interpret, right? Inferring real causality just from observed unspecific heterogeneous data is wishful thinking, in my view. You cannot do that, but you can use algorithms which are tailored towards invariance and causality, and they give actually quite promising results. We have results mostly in life science applications. This was an interesting collaboration with a famous person in proteomics, Rudi Ebersold at ETH Zurich. Okay, let me come to an end. Conclusions. Generalization to new domains, new subpopulations is hard. We don't have the full solution yet, but I think it's very crucial. We have to keep in mind standard ML is really not good at it. We have to make it different. Robustness and this invariance causality are related. They provide frameworks to improve generalization. I think personally this is an interesting relation where we can kind of link two completely different fields of robustness and causality into one common framework. I didn't say much about that, but I want to emphasize this also at the end of my talk. Validation should be done carefully. Regulation for ML AI systems is very important. I think it's a good step that the FDA requires certification of ML systems, but it's still an interesting path to go, that we have more control how good statistical and machine learning algorithms actually are. Thank you very much.
Thank you. So, is there any question?
So, thank you, Peter, for your very inspiring talk. So, I know this is not something that you really care about, but I was wondering, so you have your anchor instrumental variable, and do you have, can we hope to test that it is a source in your graph, or is it something which is completely out of reach?
What is the anchor? And then say again?
Yeah, can we hope to test that it is actually a source in your graph? Or?
No, I think this is an untestable assumption. That's a good question. So we do need to require that the environments are the sources. It's a fairly plausible assumption that you say, okay, the effect of different countries or so, they're just coming externally, but it's an untestable assumption.
More questions? So maybe at the end of your talk, you skipped some applications of your concrete examples. Could you maybe say more about this concrete example?
On what?
At the end of your talk, you skipped some slides on
yeah,
concrete
well.
applications.
Okay, maybe let me show you this. Okay, we want to interpret. That's, of course, interpretable machine learning. Let's keep things simple. How do we interpret things? So, okay, people compute correlation between two random variables or two variables which you observe. This is called marginal correlation. Then you can say, well, you go to regression association. What is the partial correlation between two variables given other variables? That's called regression association. And what we say is, okay, now you can go one step further and you can go for invariance association. And this is in the picture already a subset of the regression association. And at the inner ball of the picture is the causal association, which everybody wants to have, but I think it's unrealistic to achieve. So what I'm kind of proposing is, okay, you can move one step further instead of just looking at the regression. This is actually in the nonlinear world machine learning associations. You can go and look at invariance of that. And I maybe close here with, again, a quote from John Tukey, who wrote, one of the major arguments for regression instead of correlation is potential stability. We're very sure that the correlation, the yellow part, cannot remain the same over a wide range of situations, scenarios, subpopulations, but it is possible that the regression coefficient might. So Tukey argued from yellow to green because of stability, robustness. We typically teach this differently. We say, okay, regression association is partial correlation, but Tukey already a long time ago said, well, but it is stability. And now we can go one step further and go to invariance. If you have heterogeneous data, yesterday I had an interesting conversation at a conference dinner. If you have non-stationary data, that's good too. That allows you to look at invariance.
Okay, thank you. More questions? If not, let us thank the speaker again.
Thank you.
And since I am the last chairman of a plenary session, and also since I did not participate in the organization of the conference, I would like on the behalf of all participants to thank the organizers. And in particular, I would like to say that if it is possible to organize such a conference in Grenoble, the reason for that is that we have a wonderful administrative staff. And we can count on it when we organize a conference like that, which is very difficult to organize. So let us thank all the organizers of this conference.